Greeting learners, so we're going to continue the session. Last time we were doing exercise 6, number 4. So today we're going to take exercise 6, number 5. Determine the fifth term of the series if Sn is equal to 243 over 2 times 1 minus 1 over 3 to the power of n. Let's go to the solution. So we'll start by getting S5. S5 will be equal to 243 over 2, 1 minus 1 over 3 to the power of 5. So let's use our calculator. 243 over 2 times 1 minus 1 over 3 to the power of 5. And then we're getting 121. And after we're going to calculate S4. S4 now. S4 will be equal to 243 over 2 times 1 minus 1 over 3 to the power of 4. We're also going to calculate this. 243 over 2 times 1 minus 1 over 3 to the power of 4. Then we're getting 120. So here's going to be 120. So our T5 will be equal to S5 minus S4. This will be 121 minus 120. Then the answer is 1. T5 is equal to 1. So we're going to move to the next point. Here is the way we can determine the fifth term using this formula. As you know it, I'm just going to remind you. Tn is equal to Sn minus Sn minus 1. So now we're going to talk about something else. I'm going to clean the board and then we will continue. Okay, so we're now going to talk about the sum of an infinite number of terms. The sum of an infinite number of terms of a geometric series can be determined if the common ratio is between -1 and 1. So let's explain the logical reasoning behind this basic expression. So I'll need the number line. As you can see, this is our number line. we're going to consider 0 here. Here it will be 1. Here it's going to be 2, negative 1, and negative 2. Here we'll be having 1 over 2. And the other side, we're going to have minus 1 over 2. So it stands to reason that the number line will make it easier. If our common ratio is greater than 1, then r to the power of n tends to infinity as n tends to infinity. So a sum to infinity cannot be determined. So a sum to infinity cannot be determined. As you can see, when our common ratio is greater than 1, then r to the power of n tends to infinity as n tends to infinity, so a sum to infinity cannot be determined. If our common ratio is equal to 2, the sequence 2 to the power of n diverge. So if we consider a common ratio being equal to 2, the sequence 2 to the power of n will diverge. So what are we going to have? We're going to have here 2, 4, 8, 16, 32, 64 times 228. The next one will be 256, 512 times 2, then we get 1024. Here is the case where r is equal to 2. Now, if our common ratio is less than negative 1, see if we consider from here, then it was before greater than 1. We did consider the case where our common ratio is equal to 2. Now, the case when the common ratio is less than negative 1, then r to the power of n tends this term to negative infinity when n is an odd number, and n tends to infinity. But r to the power of n will tend to infinity when n is an even number, and as previously, our n will tend to infinity. Now, if we consider the second case, like here, when r will equal to 2, we're going to consider now if r is equal to negative 2. This is the case we're having here now. Now, the sequence is going to be negative 2 to the power of n, and this sequence is going to diverge and oscillate. What does that mean? So we're going to have, as previously here, we will have negative 2, the next one will be 4, negative 8, 16, negative 32, the next one will be 64, negative 128, the next one will be 256, negative 512, and so on. We're having a sequence which diverge and oscillate. Now, let's consider the case where if our common ratio is between -1 and 1, as r to the power n tends to 0, as n tends to infinity. So, a sum to infinity can be determined in this case. Can be determined. I'm going to clean the board so that we can see these two other cases, and then we will prove that if our common ratio is between -1 and 1, r to the power n tends to 0, as n tends to infinity, then we can determine the sum to infinity. I'm just going to clean the board and consider these two other cases. Okay, now we're going to consider these two cases in the middle. If r is equal to 1/2, the sequence 1/2 to the power n will converge. So converge. And then what are we going to have? We will be having here 1/2, 1/4, 1/8, 1/16, 1/52, and so on and so forth. If we consider the other case, if r is equal to -1/2, the sequence -1/2 to the power n is going to converge and oscillate. So oscillate and converge. What are we going to have? So here we'll be having -1/2, 1/4, -1/8, 1/16, -1/32, and so on and so forth. So now, the proof of the formula for the sum to infinity of a geometric sequence for the common ratio being between -1 and 1. So this is what we're going to try and prove now. Required to prove. Required to prove what we'll be having. The sum to infinity will be equal to a/1 minus r if our common ratio is between -1 and 1. So here's the proof. The proof is not really longer, so it's a short proof. We really want to prove that the sum to infinity will be equal to a/1 minus r, a being the first term of your geometric sequence, and r being the common ratio. So here is the proof. If the common ratio is between -1 and 1, then r to the power n tends to 0, as n tends to infinity. So we will have that s to infinity will be equal to a times 1 minus 0 over 1 minus r. Remember, the formula of the sum is a times 1 minus r to the power n over 1 minus r. So we're going to replace r to the power n by 0, and then 1 minus 0 will get 1 times a, and our sum to infinity will be equal to a over 1 minus r. If the common ratio is between -1 and 1, this is the sum to infinity. I think we're going to stop here for today. Don't forget to subscribe. If you have any questions, you can ask them. I will have a session when I'm practically going to explain. If you have any question, you can send them. Thank you. See you next time.